Ja, guten Morgen aus Fulda und herzlich willkommen zum ersten ThingsBoard User Meetup heute. Mein Name ist Stefan Müller. Ich arbeite für it-novum. it-novum, wer sind wir? Vielleicht kurz zu Beginn. Wir sind IoT-Begeisterte und wir sind Partner von ThingsBoard. Und ja, heute auch Organisator dieses Meetups rund um ThingsBoard und rund um viele spannende IoT-Themen, die wir Ihnen heute präsentieren können. Ich bin nicht alleine. An meiner Seite ist der Michael.
Herzlich willkommen auch von meiner Seite. Mein Name ist Michael Deuchert. Ich bin Data Scientist und Teamlead für den Bereich Data Analytics und beschäftige mich selbst auch schon seit mehr als 3 Jahren mit ThingsBoard. Und wir haben dort schon diverse Projekte umgesetzt oder setzen die gerade noch um.
Genau, bevor wir jetzt dann auch direkt mit den Themen und den Vorträgen starten, noch ein paar organisatorische Hinweise von unserer Seite. Das komplette Event wird aufgezeichnet. Diese Aufzeichnungen sowie alle Folien werden wir Ihnen auch gerne im Nachgang bereitstellen. Wenn Sie Fragen haben, stellen Sie die ruhig jederzeit gerne. Dafür gibt es unterschiedliche Möglichkeiten. Sie können zum einen den Chat nutzen oder es gibt hier so eine Fragen- und Antwortsektion in Ihrem Zoom-Meeting. Dort können Sie die Fragen jederzeit stellen. Wir gehen dann während der Vorträge drauf rein oder direkt im Nachgang wird es immer noch Zeit geben, auch mit den Vortragenden zu sprechen und hier auch entsprechende Fragen beantwortet zu bekommen. Ja, wir sind in der Open-Source-Community schon eine ganze Weile unterwegs als Unternehmen und haben auch schon viele Meetups veranstaltet. Jetzt das erste Mal für ThingsBoard, was ja auch eine sehr spannende Open-Source-Technologie ist. Und ja, damit wir uns einfach ein bisschen besser kennenlernen, haben wir zu Beginn ein paar Fragen vorbereitet. Damit wir einfach mal ein Gefühl kriegen, wer ist alles hier heute in der Veranstaltung. Sie sind sehr zahlreich erschienen, das freut uns sehr. Und ja, wir freuen uns eben, wenn Sie vielleicht ganz kurz diese Umfragen beantworten. Und die erste Frage ist, setzen Sie überhaupt IoT schon in Ihrem Unternehmen ein? Ja? Und evaluieren Sie vielleicht noch? Sind Sie vielleicht in der Proof-of-Concept-Phase oder haben Sie sogar schon produktiv? Wenn Sie da kurz antworten würden, dann schauen wir uns die Ergebnisse an. Oh, doch schon, also auch einige, die es in Produktion nutzen. Das ist eine tolle Sache. Aber auch einige, die noch in der Evaluation sind. Ja, dann hoffe ich, dass wir für heute auch einige für jeden was dabei haben. Wir haben auf jeden Fall ein breites Themenspektrum, was wir abdecken. Wir haben noch eine Frage vorbereitet. Dann ja, für alle die es schon in Produktion nutzen oder auch für alle, die in der Evaluation noch sind, wo sehen Sie denn die großen Herausforderungen? Das ist der Zugriff auf die Daten, erstens die Speicherung, die Verarbeitung der Daten oder haben Sie mit der Auswertung der Daten zu tun? Auch diese Umfrage läuft noch kurz. Ja, man sieht im Hintergrund, wie die Balken sich aufbauen. Okay, also an den ersten beiden Punkten ein ausgewogenes Bild beim Datenzugriff und bei der Speicherung und Verarbeitung. Und auch viele am Thema mit der Auswertung der IoT-Daten. Das ist schön, weil da haben wir heute auch Vorträge, die sich genau mit diesem Thema beschäftigen. Und zu guter Letzt noch die dritte Frage zum Abschluss. Geht um ThingsBoard natürlich. Nutzen Sie das schon? Sind Sie fortgeschrittene Anwender? Sind Sie Experte? Was können wir Ihnen heute hier im User Meetup präsentieren? Und auch hier sehe ich wieder, wie die Balken sich aufbauen. Und gleich kommt das Ergebnis. Naja, okay. Also auch fortgeschrittene User sind drin, aber auch eine deutliche Mehrheit, die sich mit dem Thema initial beschäftigen. Ja, wunderbar. Also für die Fortgeschrittenen haben wir Themen, für die Leute, die sich jetzt ganz jung mit der Technologie befassen, ist das natürlich auch heute, glaube ich, ein sehr interessantes Meeting, um sich mal einen guten Überblick zu schaffen. Ja, wunderbar. Dann gucken wir doch mal auf die Agenda. Dann können wir eigentlich schon direkt starten. Michael, oder?
Ja, das sehe ich auch so. Genau, für den ersten Vortrag begrüßen wir Vitalii. Er ist Product Owner von Trendz. Trendz ist eine eine Art Plugin, was ich auf ThingsBoard aufsetzen kann, um Self-Service-Analysen auf Basis der Sensordaten und Asset-Daten durchzuführen. Er hält heute einen Vortrag über AI und Machine Learning im Bereich von IoT. Good morning, Vitalii. Thanks for joining us today for the very first ThingsBoard user meetup. Feel free to start with your presentation and maybe with a short introduction about you, about yourself.
Okay, nice to meet you all. Thank you for inviting. So today I will tell about our experience, how to implement artificial intelligence use cases or machine learning use cases in IoT world scenarios. But first, let me start. So my name is Vitalii Paromskii. I'm solution architect in ThingsBoard. Have about 15 years experience in building highly scalable and high-loaded solutions and IoT projects. And also my specification is data analysis. So since ThingsBoard is one of the most popular open source IoT platforms, we are working with a lot of customers around the world in different sectors like smart buildings, industrial IoT, logistics, agriculture, retail, utilities, and so on. And that's why we have a pretty good expertise in this area in data analysis. And today I want to share some insights how to utilize artificial intelligence in your projects. I will tell what tasks can be solved with AI, and most important part, in what cases you should not rely on machine learning or AI. Okay, so I will start with the promise of AI. So what we can see on the market. So we see news like AlphaZero AI defeat human in chess-like games, or YouTube uses AI to suggest next videos and dramatically increase revenue using this technology, or Volkswagen Group uses digital twins, which are based on machine learning for predicting and preventing failures. And we think that artificial intelligence is everywhere right now and help businesses to reduce operational costs, improve customer experience, generate new source of revenue. But the problem is that's not true. That's not the way how artificial intelligence works, and we need to understand it. Let me show you a small example. It's from agriculture company. They had a wide sensor network that collected environment data, chemical composition and soil of mixture, amount of fertilizers they use and type of fertilizers and so on. As they want, their business goal was simple. We want to increase crop yield. And how we can do this? So they start with general data analysis and didn't find a solution how to find the optimal strategy using the data that they already have. And after that, they think, hey, we have artificial intelligence, they can help us. So we will try to create AI model that will generate an optimal strategy how to manage fertilizers. And we will feed everything that we collect. We have huge amount of data, environment, and so on. And system will tell us what to do. They took dedicated data science teams that work on this project for more than 2 years. And after 2 years, this sub-project was closed because they failed and didn't receive any output from this work. And I want to analyze why does it happen? What was the problem? Because AI solves such a lot of tasks everywhere. What did go wrong? And an optimal strategy was not found. In my opinion, that the main problem here is that people think that artificial intelligence is a magic box. You tell it what you want to receive and get an answer, and that's all. But true is that artificial intelligence doesn't know how to grow corn. It doesn't know what is good and what is bad. It cannot answer questions. It doesn't solve a problem. It's just a collection of mathematical algorithms, and that's all. And when you decide to use artificial intelligence in your project, you need to understand this, because we tend to reduce complexity of technical task. We want to avoid this complexity, and instead of solving technical problem, we expect that AI will solve it for us. It will just not work because machine learning is only an instrument and a collection, as I said, of mathematical algorithms. It's not a solution. And I want to add that this instrument, it's an expensive instrument that require a lot of resources, time, human, and computational resources. And what was the problem is that data that client collect from this agricultural project, this data just didn't have enough information how to grow corn better or how to increase yield, and that was the only problem. So they, if they understood this at the beginning, and initial analysis tells them that we do not have enough information to make this optimal strategy, they should focus on collecting additional data, additional expertise, but not on applying artificial intelligence where it's not suitable. And that's why I want to present a simple framework that can avoid similar situations in the future. So you need to define a measurable business problem. And after that, you need to analyze what data you already have. You need to analyze how data correlates between each other, how it correlates with the business problem, which is measurable. Because if your business problem is not measurable, you cannot achieve good results. You know that your proof of concept will work well only if you have some measurements that will tell, hey, we achieve our goal or not, we do not achieve it. We also need to define what data should be collected additionally if available data is just not enough. And after that, we define technical tasks, what should be done. We only after this step, we should select instrument and create a proof of concept. After that, we can move to production ready solution. But I want to mention that you need to focus on solving a problem. You don't need to rely on some instrument and think that this instrument will solve your problem. It's a standard problem decomposition process. And I want to note that you will not find words such as artificial intelligence or machine learning in this list. And it's a key idea here because we should be focused on solving business problem, not trying to solve a problem using machine learning or artificial intelligence. And as I said, we work with many companies, and mostly 90% of projects, if you expect that machine learning will help you to solve something, it is a big marker that this project will fail. We saw it 100 times in different use cases and in our practice. Second example is also from agriculture. Client has few hundred silos for grain storage. Each silo was equipped with aeration system and multiple temperature or humidity sensors installed in different levels inside silo. So this it's a silo, and this green circles here, it's temperature sensors which track the conditions how grain stored. It such happened that majority of silos were not equipped with the field sensor. And that was a problem because client didn't know for sure what was the utilization level of each silo. And they need this information for better planning. And they had two options. First option, they may find ultrasonic sensors and equip each silo with those sensors. But they will need to spend a budget for ordering these sensors, installing them, reconfiguring, and so on. And they decide that, hey, we can use AI for that because we have a lot of information collected for multiple years. And somehow this data from sensors will correlate and machine learning will learn what is the field level inside a silo. And it sounds logical because they have everything what's required. AI can solve such task. It's a categorical models like k-means can be used here. They just need to train a model that will find this correlation between sensor data and field level. This subproject was implemented pretty fast. As I remember, the prototype was created in 1 month, and after 4 months, the full pipeline was deployed on a production. Production was in Azure Cloud, and they use AI services from Azure, and pipeline was deployed using those services. And after first month, client received first bill from cloud provider for using AI services, and surprise, surprise, with such bill, client understood that they will not return investment into this subproject even after 20 years because it was not cost effective. And it would be more cost effective even to deploy new ultrasonic field level sensors instead of this model because the price was very high. And they come to us with the question what to do with this. Invest into new sensors or how we can reduce complexity of these AI models that we already have. And my team started to work on it. We analyzed historical data from sensors and found that silo field level has very high correlation with temperature deviations. So in this chart, this first chart, it has a load delta between minimum and maximum values on this chart. It represents readings from a sensor that is under the grid, those sensors. And if sensor is not covered with the grain, and if sensor is not covered with the grain, the deviation is much higher because during the night or during the day, temperature differs higher from the covered sensors. And it's very simple mathematical computations. And in 3 days after we started this work, we created and deployed very simple formula that computes field level of the silo. Only 3 days instead of 4 months. And it was simple logic. It was not machine learning. It was not AI. And it's a good example that you should use artificial intelligence only when it's really needed. Very often, I will repeat, very often you can solve technical problem using trivial logic and elementary school mathematics. I see proof of it almost every day in my work in different projects. You don't need AI everywhere. You don't need to use it everywhere because it's expensive. It requires a lot of time. And first, you need to try to solve a problem without it. AI services or platforms can solve a lot of complex tasks. But in IoT world, in reality, you can achieve similar results with simple mathematical computations and logic. It would be faster, cheaper, and with good enough quality. Artificial intelligent models can give you more accurate results compared to trivial mathematics, but accuracy is not your main goal, I think, because your goal is to solve a business problem in a cost-effective manner. In this example, I want to share you, it's about 15 years ago, NASA opened a data set about turbofan engine degradation. It was well labeled, and it's wide used in data scientists area because it's very old. We have already a lot of examples how to build models on top of this data. It's very, very popular. And as I remember, best-in-class AI models that work with this data set give 97% of accuracy. So what actually they provide? This data set contains data from 140 turbofan engines, and it contains 40 telemetries, which represent how engine operates. Yes, and each label and each time point in this data set also contains labeled data that tells how much time it remains till engine will fail. And as I said, best-in-class AI models give 97% of accuracy when engine will fail. But if let's try to analyze a little bit this model. So I visualized data from this data set in two charts. In this 3D plot, we see 4 different groups of metrics. One green one, we see that the value increase over time constantly. It do not have stochastic behavior. It just always increase. So it means during degradation process, some measurements constantly increase. And blue one and orange one, it's a metric that constantly decrease over time. So we can see a clear service degradation here on this picture. And the final group, this one, it's a purple. It's just an example of measurements that just do not correlate with the remaining useful life of engine. Same data is described on the line chart. And what if I will tell that we can apply simple static threshold logic and say that, hey, if our readings are below some threshold, for example, this one, 0.4, for example, we will also receive a simple model. It's not a rocket science, it's very simple, and we will receive accuracy of 71%. And the main question here, does 71% is good enough for us? Because mathematically, yes, 97% is much higher and much better, and we need to focus on this number. But maybe for our business, 71% is good enough. And here, sorry, and here I want to explain how to analyze cost efficiency of machine learning models on a simple example. In this example, it's from prediction maintenance also. Let's imagine that we have a project that contains 10,000 water pumps. And every year, 5% of those water pumps are broken. We need to replace them or create a expensive maintenance. So on average, every year, 500 pumps are failed. And because of this fail, because it leads to system downtime, we lose about, for average, $3,000 per each pump. And also we have a maintenance plan. And to create the maintenance, to provide the maintenance to one pump that was not failed yet, it cost us $200. And each model has 2 important parameters. They call it true positive and true negative. You can see explanation of these parameters in this table on the right. So how we should read this matrix. So on the top we see predicted failure percent and predicted okay. So this 70%, it means that in 70%, if we predict that pump will fail, it actually fail. Those 30% mean we predicted that everything would be fine, but they actually fail. So it means that our true positive rate is 70% and true negative rate is 30%. And the same is for the scenarios when pump will not fail. So we predicted in 20%, we predict that pump will fail, but it was not actually failed. And in 90%, we predict that it will not fail, it actually not fail. So, and we can create a computation because every time when our model will tell that something will fail, we will spend $200 for a maintenance. And here are our economical indicators. So without applying any prediction model, so we do not apply anything, we spent about $1.5 million per year for maintaining and for fighting with downtimes when pumps are failed. With 70% accuracy of true positives, and 80% accuracy of true negative models, we will spend almost $900,000 per year. And with 97% accuracy, we will spend $300,000 per year. So it's a big difference between 70% accuracy models and 97% accuracy models. But in both cases, it is much better than compared to our initial state. So for business, if we already have a simple static-based threshold model where we say that, hey, if value is lower than Z or higher than Z, then we need to create a maintenance. It's a naive, simple logic, but it provides benefits for a business already. And if we see that it is cost effective, that's why we don't need to spend much more time and effort to achieve higher numbers, because it will require time. But we can start with a simple model and then think, is it makes sense to make it better or not? If yes, we will work in this area. If not, we just live with this model and switch to another business problems. So let's imagine that you define your business requirement, and actually you decide that you have to use machine learning for solving this task. So let's talk about what kind of task can we solve with this. And they mostly divided into three categories. First one is detect abnormal behavior. So it means that we can identify who and why performs differently from others. We can detect anomalies, we can detect outliers in our system, we can apply some categories, work fine or work not fine, or high vibration, or not efficient operation, and so on. So just apply some categories to our assets or devices or equipment or process. Also, we can forecast behavior, and by making it, we should answer a question: should we react now to avoid failures or achieve some our goals? So we can understand when something will happen, how much time do we have, and we also need to understand how accurate our prediction, because based on those predictions or forecasts, we will make some decisions. So we need to understand accuracy. And the third group, it's a digital twins. It's a subsystem of use cases where we create a system that can give us an answer to what if question. So what will happen if you will increase the speed of production, of what would be happen if we will not, if our pump will fail, and so on. So it's a digital twin solutions. And here is a small example how anomaly detection process can look like. It's based on power stations. Red line, it represents a battery level of our power stations, and we see a big spike here in March. And so red line represents that we have an anomaly which was occur at this point of time, and we see a big degradation, and after that system stops and our power station goes offline and is out of service. And if we will apply native threshold based approach here, most probably we will set up a threshold somewhere here. So we will know in 1 week before failure occurs that system will fail, and we need to make some action with it. But with machine learning and AI, we can receive more accurate results. And as this example, this green line or gray line, it's a represented anomaly score, actually how high our anomaly is. And at this point, we will receive a notification, so much So we have 3 weeks before actual outage, and we have much more time for this. And it's a question to your project requirements. What is good enough for you? So you can spend effort creating machine learning algorithms which are complex, or you can use a threshold-based approach. And if knowing that system will fail before 1 week is good enough for you, you should stop on this. But it's just not enough. For example, you need more time. Then you spend time to create anomaly detection models and receive much more accurate results. Let's talk a little bit about detection, anomaly detection strategies, how to do this. And first, we need to start with what's actually an anomaly. So I define anomaly as a time interval when device or process behaves differently from others. Is that simple? So let's assume that we're monitoring diesel engines and collect telemetry like rotation, speed, temperature, vibration, etc. We can analyze how engine behavior changes under different conditions, and we can compare the behavior of different engines. And we know that when rotation speed is between 1000 RPM, the temperature should be 270 or 280 degrees Celsius. And we know that because such behavior was observed already 1000 times in different engines. So it's a regular behavior. And now, if we will see that under same conditions, so with the same rotation speed, the temperature is greater than expected value, it is an anomaly because it is not expected behavior. It is very simplified example that explains the basic concept used in different real-time anomaly detection techniques. So how we can detect anomalies? So first step is to split telemetry that we collect from our process or device into small intervals. The time range of the interval depends on use case, because so if your process create or if your process change behavior very fast, so your anomaly can develop in seconds or milliseconds, then you need to select seconds intervals. If your process change not so frequently, your interval may be 1 hour or 1 day. So we split measurement into intervals. After that, we will group them by similarity. So we will group similar intervals into clusters. And in this example, we have 3 clusters. So they all have different behavior. We can clearly see it, but they are similar. So we group them into clusters. After that, we can calculate the distance metric for each interval in the cluster. So it means that we can compare how far each interval inside one cluster, how far it's from one another. We can use different distance metrics like Euclidean distance or dynamic time warping. I will touch this topic a little bit later. And this distance we will use as a function to compute anomaly score, because if our interval that we extract is far from our centroid, so centroid is this red line because it's in the middle of all intervals that are inside this cluster. So if our interval is very far from this centroid, it means that it's some anomaly. And higher distance, higher anomaly we see. As I said, we can use different distance metric functions. And we observe that dynamic time warping function behaves very good in IoT scenarios because it has 3 important characteristics. It matches warped signals, it matches signals with different lengths, and it understands the behavior pattern of your measurement. And you see, if in Euclidean distance you compute how far each point from each other. With dynamic time warping, you give much more accurate results. Let me show it on the real life example. It's for water pumps, prediction maintenance mechanism. We analyze the data for different pumps and trying to predict that something will go wrong and find interesting patterns that if when pump is enabled or start working, we will see two short spikes in the voltage. And if we observe this spike, it means that we will have a problem with the pump in the nearest time. And we need to create automatic mechanism that will detect such spikes in the measurement that we receive from pumps. And so if we will compare, if we will use Euclidean distance to compare those two lines, so red line is a reference and blue line is the actual readings that we receive from pump. And according to Euclidean distance, the distance is 0.3. And using dynamic time warping algorithm, our distance would be much closer. So it will allow us to, so we will understand that it's the same behavior and the same pattern, and we will mark this pump as a failed, possible failed, with much more accuracy, much higher accuracy. What methods do we have for identifying anomalies? So they are grouped into two big categories: supervised and unsupervised. In supervised, it's a nearest neighbors, SVM, decision trees, XGBoost. So those algorithms can be used. And supervised models are great because they have higher accuracy. It is easier to compare the accuracy of different supervised models, and it's actually much easier to understand how it works, because in supervised models you need to tell machine what you wanted from it, because you have labeled data. And if, for example, we work with the prediction maintenance algorithm or use case, we will just tell, hey, this pump failed, here is historical data for this pump. And by labeling, it means that we tell an algorithm that, hey, this situation, it's a fail. And our model will train to predict those failures. But you not always have access to supervised models. And in this scenario, we recommend to use unsupervised models because they don't require such information. They do not require labeled data. Accuracy may be lower, but imagine that you have a wind turbine and you want to build a prediction maintenance system for wind turbine, but this wind turbine is very expensive. It may cost a few million euros. And the data scientist team will tell, hey, okay, let's broke this wind turbine 100 times, measure what telemetry we observe. And using this data, we can build a supervised model that will give us a metric that will tell when wind turbine failed. But it's not possible because it's very expensive and nobody wants to broke wind turbine. And the only option is to use unsupervised model in this scenario. And here is one example how to work with such cases where we have no access to labeled data. So we need to collect a baseline. So when we install a wind turbine, during first period of time, maybe 1 week or 2 weeks, we collect the baseline data. So we collect any information that we can from all sensors that we have. And we will think that, okay, maybe it is our baseline. Right now, system works fine. We assume it. And after that, we will compare new data with the baseline. And this chart, this histogram that you've seen right now, so on the vertical axis, each line represents some characteristics that we collect from the wind turbine. And blue color actually represent a baseline. And red color represent a some anomalies. So its measurement differs highly from the baseline. And we can see how our system degrade over time and color of this histogram change. And so we don't know when system will fail, but we definitely know that after this point of time, system perform differently from the original state. And that may be a marker for maintenance required on the different sectors of the wind turbine. And but working this visualization, it's important for data scientists or data analytics that can understand what is going on and make some analysis on top of this data. But end users do not require such pictures. They need simple instruments that will allow them to analyze the data set. And here's an example of a table of a prediction maintenance interface. And it clearly gives an end user an explanation what is going on in the system. So we see a breakdown by different subsystem of our wind turbine. We have indicators for metal wear, unbalanced problems, throttle rub, vibrations, thermal profile, and so on. And in this table, those numbers represent a difference between a baseline and actual observations. And here, where I draw vertical line, call it now, it means that right now we are in this state. So it's the future for us. And operator or end user can see when system or what subsystem, how different subsystem behaves. So we can localize problems. We can see that we will have a problem with the vibration and metal wear in 1 month or in 2 months. And in October, so we have 4 months till something bad may happen here. So we can plan our activity. We have enough time to react to the problem because we may order some components which are not stored in the storage, or we can acquire some technicians that can help us with solving this problem. So in this table, we understand the current state and how much time we have till something wrong will happen. And it's an example of a good visualization that's easy to use for end users. And I'm sure that it doesn't matter what kind of data analysis you perform, it should always be wrapped into simple user experience. So any user can understand immediately what is going on, what is the current state, where are we right now, and what will happen in the nearest time. So they can make action on top of this information. And you should always think about it, how your user experience would look like inside your dashboard, inside your widgets, so user can easily understand the data. And yeah, so I already talked about it. So it's a visualization of results of a model is very important for end users. So it's not just enough to create a model, machine learning model in a Python script or a Jupyter notebook and tell, hey, it seems work, it has high accuracy, and that's all. No, that's not all, because you need to provide a user interface that will allow to work with this information. You will need to provide interface that will allow to perform root cause analysis, that can allow to slice and dice data in different dimensions, find the problems, maybe find how anomalies correlate with the hardware version of your devices, or firmware version, or different locations, or under different conditions, and so on, or how it depends on the shift. Maybe you need to create some learning sessions for your operators because some shifts have more problems and another shifts has lower problems, and so on. So this instrument should provide ability to understand the data. And finally, we will focus on pipeline. So how machine learning or artificial intelligence pipeline will look like in your project. And here it's an example how data scientists see the pipeline. So they need to connect to data source where data stored. They can perform some feature engineering, clear features, normalize data, train models, compare models, and select the ideal model and deploy to the production. And that's all. Data scientists, it thinks that job is done, but it's not, because once model is ready for production, you need to actually process results of this model. You need to trigger notifications, because without notifications, user will just not know that something wrong happened. You need to visualize model output, and you should provide a root cause analysis for end user. And it is important steps. And even more, before data scientists will actually start working with a machine learning use case, you need to connect sensors, you need to collect data from those sensors, you need to pre-process this data, compute some KPIs, and you need to create a dashboard that will allow data scientists to work with the data. And so when you work with machine learning models, you need to think about full pipeline, so not only this limited part. So if I will repeat, if you create a model in the Jupyter notebooks or in Python using some well-known library, it's just not enough, because this model only exists on your machine and it's not scalable, it's not connected to production system, it's not connected with the data visualization parts, it's not notify anybody about anything. So we need to look at bigger picture and plan how your software will solve all this kind of problems. Yeah. So the summary, what I want to tell you in this presentation, the first one is that artificial intelligence is not a magic. It's only an instrument and mathematical formulas. And if you should use or try to use machine learning algorithms only when other methods didn't work for you. And you should always focus on the business problems, not on the instrument. And when you create some data analysis experience for your end users, you need to be sure that you make decisions based on business KPIs and real measurements, but not on the feelings. And I think that's all. Yeah, if you have questions, feel free to ask.
Thank you, Vitalii. Very interesting presentation. So yeah, if anyone has questions, please don't hesitate. Just write it in the chat or in the Q&A section of the chat. And yes, and there's one question, but I have one remark to your presentation, because I believe you didn't mention it. I mean, this functionality is available in ThingsBoard in the Trendz module. So we asked in the beginning, obviously there are a lot of ThingsBoard advanced users here in the meeting, but some are beginners. So this is a product or an extra product on the ThingsBoard platform, and you can use it to analyze the data. So maybe you can say 2 or 3 sentences on the functions of Trendz. So I think this would be interesting.
Yes, when I described this pipeline, how pipeline should look like, all major components that you can see there, they are present in ThingsBoard with a combination of Trendz. And in Trendz, Trendz is especially an instrument for data analysis, where you can slice and dice information, apply different filtering, grouping, categorizations. And what is more important, it has built-in models that are ready for anomaly detection. So, and the basic idea of Trendz and ThingsBoard also is that you receive an output or result very fast. So you don't need to have a special knowledge how to build models, what properties they have. You just create a few clicks, like create a nice visualization or find anomalies, and that's all. System will automatically try to do its best to make this work for you. Yes, so all required components are available in ThingsBoard ecosystem, and that's why when I explain this pipeline, I know that sometimes users tell that I have a Jupyter notebook, I can do anything, or I will take some services from cloud provider, but they are not connected between each other. So each when you select different instruments for each node, you will need to spend the time for connect them, think how to scale it in the future, think what to do if I will change my pipeline. But ThingsBoard ecosystem allow to integrate all those components together with a minimal effort. Yes, and
okay, perfect. So we have two questions from the audience. So first one is from Bernard Heider. Is the function to use Trendz-based triggers already available in the ThingsBoard Trendz?
Trend-based triggers, it would be available in version Trendz 1.9, which is released in the end of this month. So it's already tested. We are completing our test scenarios to be sure that next version is production ready. And in version 1.9, this functionality also would be available.
Okay, perfect. The next question is from Markus Frisch. Should a project start with the presentation layer and the fitting sensors, models, etc. to the layer?
It depends. You need to, when you start a project, you need to, it's better to think about two parts. First one, how this visualization presentation layer will look like for users. And another part is what data you are able to collect. And then, so you start from the data that you can collect, and on the right side, you have a presentation layer, and you need to connect them between each other. And only after you logically understand how they would be connected, so how you will transform raw data from sensors into presentation view or into set of widgets. When you understand how it would be performed, after that you can actually start implementation.
Okay, thank you. So, so no more question from the audience. Vitalii, again, thanks for presenting a really interesting topic. And yeah, I don't know if you've seen it. At the beginning, we had a poll, and we asked what are the things that are most interesting for you. It's IoT analysis, and so I would say this was a really good presentation for the people who are looking for a solution to analyze their sensor and IoT data. So thanks again.
Thank you.